Hi friends, this is the video series for your reference where myself and my friend Noah, we take a look at the Rust programming language. This series is mostly aimed at beginners with Rust programming. We're also going to cover some topics that could be interesting even if you're not a Rust programmer. In particular, this episode we're going to be taking a look at algebraic data types. And this is the canonical, really the only way in Rust to model data. And algebraic data types are not unique to Rust, but they are certainly very important if you're going to be programming in Rust. I know that, Noah, this is actually a topic that's pretty near and dear to your heart.
Right. Yeah.
Yeah, you've used some programming languages such as Swift in the past that also have these things. And some of these concepts might be a little uncomfortable for you or new to you if you haven't used a programming language that has them or explicitly calls them such. And we'll be going through, it's just some theory at the beginning and then moving into a more real-world-esque program where we sort of utilize some of these things to get something useful done. So with that, Noah, feel free to kick it off.
All right. Yeah. So, as Eric said, this is a program for beginners, and I would say I would put myself in that bucket for Rust at least. Luckily, Rust does share some similarities with some other languages I've used, like Swift. So we're going to kind of go through what are called algebraic data types tonight. And the first one we're going to start with, actually, the two most common are what are called product types and sum types. And so we'll start off by looking at product types. And I think a lot of people will find these kind of familiar if you've worked in other languages. If you're looking here now, we can see we've defined a couple here, some kind of basic ones. This is kind of similar to like what you might see with like a class where you have some property or some fields defined on the class. And the reason we kind of call this a product type is that if we look at the fields and we look at if we were to maybe instantiate one of these, the number of possible values you could have for this type is the product of the number of types for each field, or the number of values for each field, rather. And we've kind of written that down below. So if we look at employee, for example, we've kind of gone through the different. So this employee has two fields: is manager and is part-time. Since these are bools, you can basically imagine there's two values there, right? True or false. So if we look below here, you can look at our different types of employees, and you could have a full-time manager, a full-time employee, part-time employee, and a part-time manager. And you can see we've kind of gone through all the different possibilities for those fields. This is also, just to go circle back a little bit, this is how you would instantiate one of these structs. I think we had a struct in the previous episode, but it was much more simple. To give you a sense here, basically, when you define things using this kind of data in this way, you kind of you can see all the possibilities for the different values for your type. Now, of course, when you start using something like a string, you're going to get quite a lot of different possibilities, but it's still pretty constrained to certain values.
Right.
And that can be useful for basically, making sure that you don't have states that aren't possible. And potentially some of these might not even make sense. And you might want to think about, would I even want a part-time manager? I don't know. That might not be a policy at the company that they don't want people, want all managers to be full-time or something like that.
Right.
Anyway, so you can always restrict things in that way by using the correct field and basically modeling your data the way you need it to be modeled. So we kind of go, and now we're going to go into a little more complicated example, but in this case, then we've defined what is imagine a deck of cards. There could be you have a suit and a rank. And a lot of people might say, well, you could have just maybe used an integer here, right? But that kind of goes into the fact that maybe we don't want to allow any possible number here, right? And also maybe number isn't the best thing for things like these face cards, right? You might be nice to have that kind of named value for that rank. But this does actually perfectly restrict the number of possibilities to I believe was it 52 in a deck, something like that.
Yeah, and we can actually do that algebra, right? And
yeah. And we could yeah, right, exactly. So there's four. Oh, so I'm getting a little ahead of myself here, but yeah, we've used these two types here, right? Suit and rank, right? So that kind of is a good segue probably into what are some types. And unless there's more we want to cover on product types, I think we've gone through most.
I think you nailed it. Yeah.
Yeah. Cool. So yeah, let's talk about some types. So some types we could say, or variations, you can define using what's this enum syntax, or you could think that it comes from the term enumeration. And so we're basically saying like these are all the different types of suit in this case, right? Hearts, diamonds, spades, and clubs. So in that situation, we're basically saying we restrict it to that. There's no other, unless we came up with some other type of card set, like there's no other types. And then likewise for rank, we're saying, there's these number cards and then these face cards, right? And we're not doing the Joker here, so that's kind of out of scope. But essentially, I can then use these inside my struct, and then the number of possibilities. So if we remember, this is a product type, right? So if we have 4 types of suits, we could multiply by the number of ranks. And what does it look like here? 2 through 10, and then 4. I think that's 12. Is that right? I feel like I'm missing one. Jack, Queen, King. Yeah, I think that's right. So that would only be 48. So I feel like maybe anyway. So, but the idea is that I can take the number of possibilities for this sum type, and this again, the sum type means basically that the number of possible values is the number of variations for that type, and by multiplying those two, that gives us the number of types for card. And yeah, so that's pretty much I think gives you kind of a basic idea of the sum type. Yeah, Eric, you still there?
Yes.
Okay.
Yeah.
Sorry.
Right in the middle, right in the
Got
middle
it.
of that,
Right.
in the middle of that, my camera just like fell down, and I was like kind of, but I was like, he's on a roll. I can't stop him.
Okay. Cool.
Can't stop this
feel
train.
Feel free to like chime. I mean, yeah. All right. So going back, so some types, basically, you can calculate the number of values by adding up the number of types. The other cool thing you can do with them is associate some values with each variation if you want.
Right. And I think to be clear, one thing you could say is that these variations. So, for instance, if we're looking at the the rank there, they're distinct, right? So if something is of type rank, it's either 2, 3, 4, 5, 6, 7, 8, 9, 10. Ace king.
It can't be multiple,
but it can't be multiples, right? So you're very clearly disseminating one or the other thing, right? And that's it.
Cool. Yeah. So going into that, this is something I think that is like not as common in other languages, although I believe it's in Swift, and you can get something like this in another, a few other languages. But in Rust, you're allowed to basically specify an additional type that, or many potentially, many types. Mm-hmm. In like a sort of tuple idea, we could imagine something like this, mm-hmm. Where we have like 2 strings associated with this variation, and the idea is that we're saying whenever we have one of these, I don't need that actually. Whenever we have one of these variations with this, we expect to have like another value there, and that with that data in it, essentially. So when there's a parse error, for example, I expect there's like some string associated with it. Maybe this is like the string that has the parse error or something. Or the character error has the character that's wrong. And so that's kind of can be pretty powerful when it's used with what we're going to see in a minute, is the match operator. So when you process these data types, you can pull out this data,
right,
and kind of drill into what you need. And then as we get further into this episode, we'll see that you can do a lot of cool things when you're parsing strings, for example. Okay, so the next two that we defined here are actually kind of types that are already given to you in Rust. The result type and the option type, we've kind of prefixed it with my, just so that doesn't collide with the existing ones. So my understanding is those are like always available to you, if you need them, and it's basically a common way that you do kind of like error handling with results, for example. And then also like with parsing, we might use the optional type. So you might see these types a lot, and they're just called result and option.
Right.
But this also brings up another part another thing that in Rust that we can use called generics. So these sum types are now defined over two generic parameters. And so we're saying that this my result has two variations, right? It's either okay or it's an error. The okay can have some value with it. So we can define whatever that is. We can define the type. Whenever we define a result, we can define, hey, this is going to return values that are strings, or this is going to return values that are, cards that we just defined up there, or whatever it is. So we do some processing and something comes out, and it's either an error or it's okay with the value. And the error also could have the actual error value. And so if that I don't know if that makes sense, but we can use this operator called match to actually process this. Match is a built-in function. So this is again something you get for free, kind of similar to what you would use for use in other languages. Like it's kind of reminds me of switch in Swift, for example. And what this does is basically lets you enumerate overall the different possibilities for your whatever your type is. In this case, we're iterating over enumerating, I guess, or matching, a pattern matching, let's say, our result. So in this one, we've kind of contrived it. So we've made and we had to use some kind of complicated syntax here, but mostly to get not that compiler happy. But we're saying this is an okay result, right, with a hello in it. So it's got a string and my error, which is another type we've defined here. And in this case, it's always going to be okay. But so if we ran this, we would expect to see like hello world. And so the way this works is if it matches the first one, then it follows or runs this code after the kind of hash rocket symbol here. Yeah, Eric doesn't like when I say that, I think, but
what do you mean I don't like when I say
I don't know. But
I've never heard anybody call that the hash rocket before.
Really?
No, I think I've heard.
That's like all I actually heard it at my current job the first time.
I thought it was fat arrow. Fat arrows.
Fat arrow, I've heard that too. Okay. Yeah. And now I'm gonna go look up hash rocket after this to make sure.
I think in Rust, Rust lingo and specification calls these arms. These are arms of the match operator, right?
Okay.
Yeah.
Okay. Cool. Yeah. So anyway, in this case, we're gonna get hello world every time. If we did change this to be an error, we would get error returned. Yeah. And here we're just printing it out.
Right.
All right. And then the next one is a little more simple, but also one that you see a lot is the option type, or in this case, my option, since we're just we're naming our own, and that can be some or none. And so if we think about some, it means basically there's something there, or we got nothing there. And often you use this when you're maybe parsing something and like you don't get what you expected, so you would just return none and say basically some error happened and we just we don't care about the error, we just
Yeah.
want to continue maybe.
And this might be somewhat similar to how people use null in other programming languages, right?
Yeah, exactly.
Right. So you either have the thing or you have null. This is how Rust encodes that kind of notion of null. There is no null in Rust. There's just the option, for instance.
Yep. And if you have the sum, then you basically have that associated data. And here we're matching again. Similar thing going on. Another thing to note here, which I maybe didn't mention, is when you have this like statement here with no paren or no brackets or angled brackets around it, you basically just returning that back to like wherever your result is.
Right.
You can also like do, and we'll see this later, you can do like a return out of here, and that would actually return out of like the calling function.
Right.
So that's just another thing to note about Rust. I think is a little different, but and then in addition, there's all right. So going back to the option type, in this case, we just said it was none, so we would expect to get default out of here. So yeah, that's kind of I would say most of the theory that we're going to talk about today.
Right.
So just to recap, we've gone through product types and sum types, and then some types with associated values. And now I think the next part we're going to kind of build a smallish program to parse some math expressions, basically plus and minus. And so we're going to use a lot of these types in that program, and I'll give you an example here of what it's going to do. So hopefully you can see my terminal here. And if I run, this is the working program. So this is what we're going to build. So there we see it did like 2 + 2 = 4. So it takes in these expressions, and you could also do -1. We get 0. So let's start on that. Unless Eric, there's anything you want to say about these types?
No, I think you pretty much nailed it on the head. And one thing that I will say that has worked out well for me, you sort of touched on this in the beginning, which is that when you constrain your program to be very, very explicit about the kinds of data that can be represented, you can make your program sort of correct by construction. Right. So in the example of the card that you were showing at the very beginning, because we chose not to use a integer for a rank, there is no value for the type card that actually isn't a representable real card. If we had chosen to use an integer, for instance, like what if rank became 50 for some reason? That's actually legal within the type system, but what is a rank of 50? Like that doesn't make any sense. So I will say that this can be very useful if you're trying to really be particular about how your program operates. And there's a famous talk that I think it's famous that you and I have spoken about many times. It's called "Making Impossible States Impossible," which is just to say that there is no such thing as a card that isn't a real life card by construction, right? And so for things like testing, reproducibility, understandability, all these kinds of things, this is awesome, right?
Yeah. No, I've since I've been kind of introduced to this concept, I definitely went pretty wild, like using this, and like definitely felt like I I was writing better code, I think.
Yeah.
So
Yeah.
because of that.
And also, just as a side note, this is more particular to Rust. By the way, algebraic data types are available in many programming languages, especially functional programming languages and programming languages that have pattern matching in general. Rust is definitely not a functional programming language, for instance, but still has them. And probably the reason it has them is this is a way in which Rust can continue sort of its philosophy of safety. Right. Right. Like, Rust offers us many kinds of safety. And some of those are like representational data safety, right? Like the consistency and the correctness of our data. Is better because it gives us tools like enumeration types, like sum types, and product types as structs, right? And so we can actually make our programs safe in this way, right?
Totally.